Hello guys, in this video we are going to discuss the three different types of bonds. Let's start talking about what a bond is. It is a force that holds atoms together. Forming a bond will result in new properties that are going to be different from the properties that normally we would observe on the individual elements. So the properties that we associate with substances will heavily depend on the type of bond that they have and also the elements that are involved in the bond. The three different types of bonds are going to be metallic, ionic, and covalent. In this video, we will discuss all three of them. Let's start with metallic bonds. Now, metallic bond is just really an array of positively charged metal cores, so basically any kind of metal that has protons, that is surrounded by a sea of electrons, or in other words, delocalized valence electrons. Now, here, whenever I mention and I talk about free-flowing electrons, I'm talking specifically about the valence electrons that are normally found on an atom of a metal. Now, if you think about it, most metals have only 1, 2, possibly 3, maybe 4 valence electrons. And the entire reason, the purpose of forming a bond is to have a full octet. So a total of 8 valence electrons. Now, atoms will either transfer, they will share electrons in order to gain a total of 8. Now, like I just said, most metals don't have enough. So another reason that this entire sea of electrons is taking place that we observe on metallic bonds is that all of these atoms actually are going to have very similar electronegativities. So one atom is not going to outpower the other because their electronegativities are going to be very similar. So because there's also not enough valence electrons around to ensure that everybody has a total of 8, the electrons are basically just kind of free-flowing all around. And that's really what helps account for a lot of the properties that we observe on metallic bonds. Things like malleability, ductility, and the conductivity of both heat and electricity. Now, let's talk about malleability, which is just the ability of changing the shape of a particular compound, or in this scenario that we're talking about metals. Now, all we really have to do is rearrange how those atoms are in position. And we can do this by a couple of ways. Most of the time, it's going to be through pressure. Ductility is the ability for a metal to be able to turn into things like wire. And again, because the electrons are not tightly held onto atoms, it's very easy through pressure to be able to modify the arrangement of those atoms and therefore the entire substance. When it comes to the conductivity of heat and electricity, well, both of them are dictated by the movement of electrons. So the entire sea of electrons is the explanation as to why we observe the properties that we usually associate with metals. Now, if you've ever encountered things like brass, bronze, stainless steel, sterling silver, you might notice, well, those are not on the periodic table, but yet they're still metals. Well, yeah, they're not on the periodic table because they're not pure substances, but they are regardless made of metals, and we call them alloys. Alloys are homogeneous mixtures of at least 2 metals. So it's basically a solution that is a solid in a solid. So we are basically mixing metals at very high temperatures. And we do so as society because there are some properties of metals that we like and some others that we don't like as much, but that if we were to add a specific amount of another metal, we can either make it stronger, make it shiny, or prevent it from oxidizing, which is really the main 3 reasons why we tend to create alloys as society. So before we move on to talking about ionic compounds, I need to refresh you on cations and anions. Please remember that in order for us to produce or create a cation, electrons have to be lost. An anion, we have to gain electrons. And if you guys remember back to our unit on ions, we discussed the reason for atoms to actually gain or lose electrons. And again, it goes and circles back to the octet rule, having a full valence shell. So that's what we really are going to be discussing here as we move on towards ionic and covalent compounds. So before we move on to that, we do need to again discuss oxidation numbers, which is just the number of electrons that are either lost or gained by an atom to achieve the octet rule, so the full valence shell configuration. Here on screen, you guys have a mini version of the periodic table with the oxidation numbers that are associated with the main groups. So please take a moment, take out your periodic table, go ahead and label it with the numbers in the circles that are shown here on screen. Let's talk about ionic bonds. They are electrostatic interactions between ions of opposite charges. So we're talking about positively charged ions, aka cations, and negatively charged ions, which we know are called anions. So for ionic bonding, is formed basically through the transfer of electrons. Now, the electrons are transferred, like I just said, to achieve noble gas configuration, having a total of 8. Now, ionic compounds are made up of really just two things, and we can really talk about them in different ways, but I do want you guys to have the three different ways that you will see them referred to in the future. It could either be a positive and a negative ion, which we know are called cation and anion respectively, or also more in a general way, metal and a non-metal. But regardless of how things are defined, we're still talking about the same composition. We're talking about opposite charges, basically. Now, for the properties of ionic compounds, they are going to have a repeating arrangement of ions in the solid. We call it a crystalline structure. And what I mean by that is that we're going to have a positively charged ion, a negative, positive, negative, positive. And in the next level of the structure, because we have a positive, we will then have negative, positive, negative, positive, negative. And that repeating structure is just going to continue throughout the entire sample. That's what we call the crystalline structure. Now, because of this entire opposite charges, the bonds are going to be very strong. The positive is going to be highly, highly attracted to that negative. And that is one of the reasons that they're easily dissolved in water. Now, we have not discussed polarity just yet, which we will get into that in a later unit. But for right now, that's a property that we need to associate with ionic compounds. Now, because they have this very strong force between the ions of the positives and the negatives, in order for us to melt ionic compounds, the amount of energy that needs to be added to the system is extremely high. So their melting points and their boiling points are ridiculous. They're very, very high. And again, it goes back to that idea that once those electrons have been transferred from the positives to the negatives, and the full octet rule has been met, so having a total of 8 valence electrons, breaking apart those bonds is going to require a lot of energy. So rarely do you ever see ionic compounds actually being melted unless you actually put them under a lot of pressure at the same time. So we associate high melting and boiling points to ionic compounds. Now, when it comes to covalent bonds, it's slightly different, but the purpose is still the same. They are formed when we have two or more nonmetals, in other words, anions, with similar or small differences in electronegativities. Now, if we recall electronegativity, it accounts for the fact that some atoms are better than others are at attracting the electrons of other atoms. So because we're talking about nonmetals that have very similar electronegativities, one is not going to truly outweigh the other in terms of, again, electronegativity. So what is going to end up happening is that those electrons don't really have a preference of going to one atom or the other. So what results is sharing electrons. And that is a property that we associate with covalent bonds. Now, nonmetals are going to hold onto their valence electrons because they still need to have that noble gas configuration. Now, sharing allows atoms to count both the electrons towards all of the atoms that are involved in the bond. Now, some of the properties that we associate with covalent bonding is going to be that they can exist in liquid, solid, and gaseous states. They're going to dissolve easily in the water, and again, it goes back to the polarity that we haven't quite discussed yet. And because they're sharing electrons, that bond is not as strong as the one that we would normally observe in ionic compounds. Now, for the covalent bonds, those melting points are going to be very, very low. And if you think about it, if they can exist in liquid, solid, and gas, it means that under normal circumstances, those melting points and boiling points have to be pretty low. Otherwise, they would all be solids as we would normally observe with the metals, with the metallic bonds. And because here we don't have any free-flowing electrons, we are then consumed that covalent bonds are not going to be very conductive to electricity. Here on screen, what we have is a table with an overview of all of the different types of bonds that I believe is going to be a really good reference for the future. So if you would like to at this time either jot it down on your notes or at least take a picture or screenshot it so that you can have this as reference for future. In our next video, we are going to learn a little bit more about the ionic compound and the rules for naming them.